Hello, everybody. My name is Kevin Kotchek. I'm the founder CEO of ChemicalQDevice. Here to tell you about episode 59. This is December 1st, 2022, in specific on QML product development for neuroimaging / Alzheimer's. So I'm going to go over a bunch of stuff. There's been very good news on medical imaging, three different press releases, basically Google, Amazon, and Nuance. I'm going to go over some coding. So this is basically the Qiskit IBM. I'm going to go over the Pennylane and Classiq as well. And then I'm going to be tying a lot of the pieces together for quantum machine learning and what makes sense in business. Now, as you can see here, that imaging data accounts for 90% of all healthcare data. Over 5.5 billion global imaging procedures exist per year. And there's an average imaging study size has doubled in the last decade. Multiple copies of the same imaging data are stored for both clinical and research purposes. And advanced imaging data analytics can take weeks and or months. Now, the global AI and medical imaging market is expected to grow at a compound annual growth rate of 45.68% during the forecast period 2022-2027. Neurology has accounted for the dominating share in the industry. That's a Yahoo Flash report linker. And this next slide will help to further explain this. So basically, this Google Cloud is October 2022. And in specific, it says potential for 80% less lines of code. Now, assumably, these are mostly still conventional or classical approaches, especially with medical data that the standards need to still go through for quantum. Now, the Google Cloud is their newest medical imaging suite. So these are big products, anywhere from image storage to image lab annotation. And you can just see the number. So I'm looking at this first column for Google Cloud, building AI capabilities with the support of image-based clinical diagnosis. And then just the number of users that there are. Now, the Amazon Health Lake came out this month, so November 2022, the update. They call it Next Generation Imaging Solutions. So in specific, you're talking about 40%, storage costs being reduced, and then sub-second medical image retrieval. So these announcements are quite something. I also included a link in the, it's somebody else that kind of referenced these three articles. Now, with NVIDIA Nuance, this first one kind of sums up a lot. So Nuance is a Microsoft company, and then NVIDIA, you'll see this MONAI, so that's their open standard. So MONAI has only been around since 2020, so only 2 years. And a lot of this is basically taking a lot of the work out of neuroradiologists' hands. And, with artificial intelligence and machine learning, basically getting better approvals with HIPAA. Now, the Nuance article reduces model adaptation times from years to weeks. Domain shifts in data now takes weeks instead of months. Issue detection and repair takes minutes rather than hours. So these are general terms that basically computation is, and especially for medical data, medical imaging data is evolving and has evolved. And then you can see, so waiting period from days to 15 minutes. And then the MONAI open source AI framework is consistent through some of these other ones as well. Now, a lot of people say, okay, so say if you're new to quantum computing or not quite, up to date with healthcare, is the attention, this is Monroe's motivated sequence, and I made one for quantum machine learning. The attention is, in 2019, there was Google quantum supremacy, first ever over conventional that we know of. And then in 2020, AWS announced that their public cloud service is available. In 2021, the first pure play quantum hardware company IPO'd for $2 billion. And then this year, with this push for medical and quantum, Cleveland Clinic at IBM basically having the first quantum computer in healthcare on Cleveland Clinic site. Now, the need for all this is we need new quantum machine learning neuroimaging algorithms. And in specific, the satisfaction will come from improved Alzheimer's prediction. And I'm going to get into that in more detail. Visualizing all of this is basically Fermilab is building a new quantum computer and new quantum sensors for MRI analysis. As you can see the picture here with the attendee, overlooking the MRI. And this QSI is also looking at diamond quantum sensing to improve, sensitivity in MRI as well. So just imagine that picture. And the call to action is basically this commitment with quantum transfer learning developments. So I updated this. So this is the stage 1, stage 2, stage 3, and stage 4. I'll mostly be talking about stage 1 and stage 2. So in stage 1, this is a software approach to taking existing, such as ADNI databases, which is Alzheimer's images or brain images that say yes or no. Basically, to insert quantum technologies as necessary to get better patient predictions from, say, like a mild cognitive impairment to Alzheimer's disease, and that's one of the papers I'm going to be focusing on. And then stage 2 is basically this same quantum machine learning approach and an option for hardware such as diamond quantum sensing, which is kind of taking off on its own. Stage 3 is synergy between those two, an option for standards and protocols. Stage 4 would be FDA submissions pending, the standards that need to go through, such as IEC, NEMA, in order to start incorporating quantum tech that run off quantum computers and quantum simulators. Now, the key milestones are basically getting collaborators, partners, neuroradiology, imaging experts, healthcare, quantum machine learning experts. They exist. And then a building to kind of put all this together. And then FDA requires organizational excellence. So this would basically be working towards program performance, governance, and operational efficiency. Now, a lot of people don't know even much about machine learning, so I put this together. So there's a source that I cited with this, the 16. So machine learning is able to learn and adapt without following explicit instructions on conventional computers. This uses algorithms and statistical models to analyze and draw inferences from patterns and data. Now, quantum machine learning incorporates quantum algorithms into quantum technologies such as quantum computers and quantum simulators, and can maintain a portion of original machine learning programming for hybrid applications such as quantum transfer learning, which is likely. So this first paper I'm going to take a look at, it's basically Alzheimer's machine learning, and they look at all these, I'll just read the headline here. So machine learning methods for predicting progression from mild cognitive impairment to Alzheimer's disease dementia, a systematic review. So this is basically the last 10 years, over 100 qualitative studies with machine learning and neuroimaging. And it's the prediction, if you have an image, what's the chance or the likelihood of it going from a patient that has mild cognitive impairment to AD? And then it looks at all those. And then obviously the most recent studies tend to be the most accurate. So it's the accuracy of that prediction if the patient, will form worse dementia. And in specific, they use MRI, PET scans, MEG, and then this ADNI is a trusted database. It's been evolving over the years. And, basically, you're going to get your best results with deep learning. Multimodal means that if you have, both MRI and PET, as opposed to just one or the other, multidimensional. And for this to basically go clinical, and this is conventional computing, this article, as you can see, was late last year, is that, more samplers are needed, not just this typical Alzheimer's disease neuroimaging initiative. And as with everything, conventional computer gets better neuroimaging gets better as well. So this is basically the selection criteria they use to form additional charts off of. And it basically starts with this, PubMed, PsycInfo, WAS, 663. And then they're looking at the bottom, the 116 best. and then comparing it. And as I said, the trend is basically if you have more like an MRI and PET at that same time, those neuroimages, multimodal, and then the newer studies tend to fare better. And then also, the ones that incorporated deep learning. Now, as you can see, automated, so this is the second paper. I've taken a look at this before in this discussion. I'm going to take a briefer but more detailed look at it. Automated detection of Alzheimer's via hybrid classical quantum neural networks. So this would be like a QNNs or hybrid classical QNNs. And it's basically, it didn't go as far as say, the establishment is basically, you can look at somebody that is a healthy control, that's advancing in age basically to mild cognitive impairment. And then you can have all the way up to Alzheimer's disease. And then this one looked at specifically, this is kind of like a new approach using quantum, but it's just looking at Alzheimer's versus healthy. So the numbers are going to be a little bit higher than if you looked at, like, say, from mild cognitive impairment to Alzheimer's disease. It's easier to see basically what they did. So they looked at 6,400 MRIs, and then in specific, this is quantum transfer learning with a quantum variational circuit. So it's basically keeping a lot of the conventional algorithm, and then incorporating quantum aspect to it. Now, the keys here basically is that Pennylane, they're known, it's an open source of a hardware company in quantum called Xanadu. Their performance over two different Qiskit simulators. So they focus on QML. So it kind of makes sense that was the best result. I'll show you the chart. Now, this 97% classification, what that means is it's able to classify between a healthy control and an Alzheimer's disease. They said 97%, as opposed to their own 92% classical method. So this will likely have to take further investigation as far as the definitivity of the quantum advantage here. And they say, as most papers do, is that it has a potential for clinical applications. Now, keep in mind, as I mentioned before, they did not look at mild cognitive impairment, and that's a typical binary. You can look at all three. You can look at AD, MCI, MCI-HD, healthy control. And then, basically, once real quantum computers get better, then you can start wean off the simulators. Now, a lot of people might say, okay, well, you either have a quantum computer or a classical computer, when in reality, you can have multiple areas. So this first one is basically starting off in this classical layer, ResNet 34, 512 feature vector, and then going into a quantum variational circuit. Now, the quantum variational circuit, this big box in the middle, is what runs on the quantum simulator. As you can see where it says, you have your circuit and it's going to the circuit device. Now, you can see it goes back to a conventional approach too, and then this is where you can classify whether it's demented or non-demented. So using their methods, they said 97% accuracy for the quantum transfer learning, and then 92% if they just did it classically. So it's a good study, but it's something that will likely get built on a lot more. Now, here's the data as far as the Pennylane simulator versus Qiskits. Now, the two Qiskits, the orange and the gray, are IBM open source. They're perhaps known a little bit better than the Pennylane, but the Pennylane focuses on quantum machine learning, and you'll see the blue at the top, which was better. Now, here's basically instructions. So I took the foray and I logged onto Qiskit and I ran a circuit. I'm going to show you all this. This is basically Pennylane, basically saying how to create a quantum machine learning program. So you can see define quantum circuit, post-processing, cost function optimization, and these steps, it's an iterative process to get the best. But this is one approach, is to go the Pennylane route here too. So another one here, so Classiq is known for basically simplifying things. So this is, in all of these, I abbreviated the main document. So anywhere from, it's really a step-by-step, open your code, open command palette, and then all the way down to analyzing your circuits, modifying code, and overcoming constraints. So this is another approach here too, is a classic. Some of these you take your circuit, like you would, hire Classiq, and then you would run on IBM. And then this, for instance, is an IBM variational classification instruction. So set training data points, classification circuit, all the way down to number 8, classical optimizer. So this was done, I think it was, they have these conferences, basically, these Qiskit, and it was a student of it. And of course, it's probably been checked over. Now, this is on the more, so you have hardware, software. It's same thing with conventional. So you have, so IBM is known for their quantum data centers, 20 quantum systems. So President Biden, say for instance, was just up there, and IBM's putting $20 billion, not just into quantum, other technologies too. So their big thing is basically this error suppression, error mitigation is being baked into Qiskit, and then the processor. So it wasn't available on my view quite yet. It was it's this upcoming 400 qubit, and it's modular to over 16,000 by the end of next year. So you could see additional improvements coming. They stick to their forecasts pretty well, or at least it has been the case in recent years for quantum. So 2023 quantum serverless, and then 2024, 2026, this intelligent orchestration, circuit knitting, toolbox circuit libraries. And so I'm going to go over, so basically they say 2.2 trillion circuits have been run on IBM quantum systems. It's a huge number. A lot of people believe in the IBM ecosystem here. So this is the circuit that I ran. They say it's Bell State. And so the first one is quantum circuit diagram. So it's like a musical notes. It's called staff notation. So you have different gates, so Hadamard gates, and then different qubits can be entangled to other qubits. So that's the one on the left. On the middle is the key. It's called OpenQASM 2.0 code. So this is what tells it, what the diagram is going to be, all these types of things. And on the right, OpenQASM, I believe, gets translated into IBM Qiskit code. So this is a simple circuit to show basically it's free to access on the lower quantum hardware. So on the left are all the quantum computers and simulators I mentioned. The 127s are Eagles, and then in specific they'll have your Washington and Kiev and Ithaca. And I'll go over some of this a little bit later because there's kind of like a hot topic. Now, when I first ran, it said it would take 5 hours. It didn't. It was quicker than that. But the middle diagram here is basically a run in progress. And then in specific on the right, run completions, you see, the whole thing took 4.7 seconds to run on a quantum simulator with a circuit that it suggested for me to run. So tying a lot of this into the business world is basically, I took this course. It's a Harvard University, Innovating in Healthcare. And the lady that ran it, very thorough, a lot of examples as far as classification of companies. And obviously, I'll get into that a little bit more. But these are just key things to think about as far as anything, and especially with an emerging technology with quantum, and now you have healthcare, does this company do good and well? So meaning, are they beneficial to health? And then do they also do well financially? And in specific, so is the company a first mover or fast follower? ChemicalQDevice may be viewed as a first mover in some regards. What is the depth of research that has been done? And then number 4 is kind of relative to it. How well can they describe the black box? So this is somebody, the investor comes in, what is this thing? And, are you stumbling over your words or do you understand it? And then number 5, is the product currently cost effective? Now they go, or in this specific program, it's these 6 factors. What I did is I projected ChemicalQDevice, and keep in mind, this is still early, but you take a look at things such as structure, see your partners, competition, finance, who's it been funded or who will likely fund it, public policy. So I've been talking about this. So this is the say, for instance, ISO, ASTM, IEC, NEMA, and then prospectively, this FDA would require these regulations on the quantum side, with FDA kind of taking more of the patient safety approach and the hardware, software being other regulations. Now, they say, is it consumer facing? So it's not, it's business to business. So the perceived value would be basically how good is the prediction over today's conventional approaches. Accountability is basically would be, say, did you pass your regulations, for IEC and NEMA to be qualified for FDA? And then for technologies, software for hybrid classical plus quantum. And there's a number of ways of looking at this, but basically what's often viewed is like, is the company more, does it have technology? Is it more consumer facing? Does it have public policy benefits to it as well? So some of you may know, this is a flywheel. So basically the way that it works is you see in the attract and stranger side is that you have acquaintances come in. Now, this goes into basically a business funnel too. So the strangers to prospects is going to be a lower number of potential business partners or customers. And so at that point, they're engaged. Okay, so a fewer number of prospects go into customers. The customers are both engaged and delighted. And then the promoters are interesting because they can, they speak on it and they can help bring in new strangers, which, so basically you could apply flywheel force, which your business scales. You can apply flywheel friction, which slows the process. And scale refers to business growth faster than investment growth. Now, the key is to watch for changes in customer behavior and throughout this process. Revenue operations, and this is a course I took from HubSpot, they say it's the people, processes, systems, and data that control how businesses generate revenue. So you basically have to become an expert on all these diagrams and understanding them and how to manipulate things to speed up the flywheel or slow it down. So here's the sales funnel. So it kind of ties in with the flywheel because more people start at the top. So this is prospective, clients, they're basically aware and they have interactions. And then you go further down to interest, evaluations, negotiation, to closing of sale and payment and renewal of contracts. So at the bottom, the number of customers you generate is going to be, you'll have less renewals than closings of sales. And then you think about this process of how to enhance it from top to bottom. Now, there's a Stanford course out there that I recommend to any young entrepreneur or basically early entrepreneurs. And they say these things that ChemicalQDevice follows. So be caring, sharing, and daring. These are important concepts. If you're not sharing, chances are your material is not that great anyway, but it's important to keep getting it out there. Now, they say the best leaders are self-aware and moderately assertive. And there's a famous quote by Tommy Lasorte says, I believe managing is like holding a dove in your hand. If you hold it too tightly, you kill it. But if you hold it too loosely, you lose it. And there's some humor tied into a lot of these things as well. Now, number 3, it says the best bosses protect their own people from harm. And they say to use small wins and also with long-term strategies, such as big, hairy goals, or we call them BHAGs. Now, there's Linus Pauling once wrote, so he says, to get a good idea, you need a lot of ideas. And that's just the case. And I'll get to this a little bit later as well. Now, number 5, allow employees to act without asking for permission first. This quote is by 3M's William Coyne. He says, after you plant a seed in the ground, you don't dig it up every week to see how it is doing, meaning allowing some autonomy for your employees. And number 6, employees are multi-team systems. The team needs a definite project. You need to have knowledge diversity, meaning your group, if it's a small group, and especially should have different functional experiences. And you should mix novices and experts together and mix optimists and pessimists together. So it's not looking at things like negative, it's just the way things are. Now, this MITx, Becoming an Entrepreneur course, is also good. They said the same thing. Share a lot. It is hard to duplicate your skill, interest, time, and team regarding a potential competitor. Now, what this means is that it's very hard for somebody to take what you're talking about, your documents, and directly translate it into something that they have your skill, they have your interests, they have your time, and they have your team. Now, they say you don't need all the answers or perfect idea or more experience. You just have to follow simple rules. So they say do ample amount of research, customer interviews are key, internal research surveys, and then when would the customer most likely make an impulse buy? Now, I recently finished this course. It's a University of Maryland. I've audited all of these. Um, Achieving product market fit. They said don't make the product that would wind up to be too expensive, to take too long to make, or be too risky. Now, minimum viable product should have performance, benefits, and delighters. So that's interesting when you think of algorithms. How can you have a delighter for your algorithm? But these things exist. And then number 3 says companies create value through a value proposition that meets customer needs. Now, this is basically product market fit. And at the bottom, my target customer that I've defined for ChemicalQDevice, going from outside in is it's business to business, so it's not business to customer. And then it's healthcare related, medical imaging related, and then specific neuroimaging, and then specific existing neuroimaging AI ML platforms such as the Google News, the Amazon News, the Nuance News. So you go up from the bottom and you have underserved needs, and then product market fits in the middle. And then you have value proposition, feature set, and then UX. And the gentleman that ran this course said it's so important to get the bottom right, your target customer. So going all the way up to the top would be stage 1. So this improved predictions. So this could be, say, for instance, a better results for mild cognitive impairment to Alzheimer's disease. Now, this one is interesting because a number of us have seen this, but the way they put it, the frame of reference, is if you're in the late majority, meaning this conservatives, you purchased your first iPhone after 8 years. So, and then that still leaves skeptics to the right. So I thought that was interesting. But a majority of this, as far as going into the mainstream market, will likely sit, and I believe this is for total percent, like population, like buyers and consumers. It will likely sit with tech enthusiasts, even medical, and then your med tech, and then, obviously with quantum computing, at least for the beginning portion here. Now, University of Maryland also said the customer has pain points. These are unmet needs, such as customer dissatisfaction. This is apparent in interviews, as I mentioned before, product reviews, posts, or unarticulated need. So now we're starting to talk about quantum, or unaware of new technology and capabilities. And that's totally quantum is, if you're a startup in quantum, you're educating a lot. Now, I've been mulling over this a lot. It's basically, you usually see the star in the upper right-hand corner, but not this case. So you actually want low user satisfaction for potential product and high importance to the user. And that is where you find opportunity, this upper left here. Now, this totally makes sense to me. So this process of envisioning, building, measuring, and learning, and many startups, they can quit an idea. That doesn't mean they could quit the company, but, I've had to pivot twice. I've had a provisional medical patent. I've had a quantum-based patient monitor, and I couldn't quite define all these things. And I'd interview other people, and basically this is where the quantum machine learning neuroimaging kind of being in that pioneering field. Now, the whole goal with this is to not keep pivoting or quitting, is to move down to perseverance and then scaling. So this is business growth outweighing investment growth right there. Now, this is where if you have issues, which you will, and I started to define some of these. So this is called the fishbone. So the fishbone diagram, I believe it's Japanese, so it's Karo Ishikawa. And the straight arrows are primary causes, secondary causes are the diagonal ones. So they call it also the 6 M's. So you can call it like manufacturing, but in this specific diagram, it says equipment, process, people, materials, environment, management. And then you can see the equipment is obviously going to be cloud-based quantum computers and simulators. So imagine if there's a power outage, these types of things, how are you going to deal with it? The process is basically the quantum data and medical data dynamics and, the synergy between the two. People, healthcare imaging staff, quantum data programmers, Number 4, materials, pre-existing neuroimages, local computing allocations, environment. I believe this is right. So controllable or random, it could be something like, internet, and regulations aren't random, but at that same time, part of the environment. And obviously you have other pieces of management as well. Now, this book, I go to all these tech coffees in town in San Diego here. It was recommended to me. And when I first picked it up, I have the audiobook. I could not follow it. I could not understand it. It's completely different language than what even mainstream business might follow. It's a very specific thing. But the titles, this is by Brad Feld and Jason Mendelson. Be smarter than your lawyer and venture capitalists. Now, venture capitalists are generally on the founder's side. They want the company to do well. It's just the terms. You want to make sure that you understand things. Now, they say early on you want an experienced, accredited, engaged investors to begin with. So you can't have, especially for a new quantum technology, there are quantum investors out there. They say be aware of existing precedences. So this is for me, it'd be AI, ML, algorithms, neuroimaging. So they say the entrepreneur is the center of the entrepreneurial universe. Oftentimes other investors have many other companies that they look at, and you're spending the bulk of your 60, 80, 100 hours a week. And they say take a look at the back of the term sheets. The term sheet is basically something where they say, okay, we propose this, and then you have 30 or 60 days to look over it and then agree or not agree. And they say watch out for them adding legal fees. And then there's this, as especially an early entrepreneur, if somebody gives you a term sheet, they may put a no-shop clause in it, which means that they can't, that the entrepreneur cannot go to other investors during this 30, 60 days. And then there's just things out there such as this is market, or this is how we always do deals. And they say be cautious of party rounds. This is a lot of investors. If something goes wrong, you literally have to chase after everybody, the sheer number of people. They say avoid this term material and term sheets and scenarios where entrepreneurs are left without benefit. So they say this, 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 and this, and then it's business. So I've covered this one before. I added this week. So we see number 1, IBM Cleveland Clinic, obviously 10-year partnership, first to do quantum computer in healthcare in recent months. NYU Langone, this is a hospital in New York, and this is, I kind of mentioned this with one of the earlier slides, but basically, making new quantum computers, these things are happening, and making new quantum sensors for better MRI analysis. Number 3 is the one I added in this week. So I actually came across this earlier. It's quantum diamond sensors for increased MRI. They're likely working on a lot of other stuff too. But I would say kind of 2 and 3 are kind of like the big organizations that kind of reflect the sentiments of this startup. Number 4, Mount Sinai Hospital, Sandbox AQ. This is cybersecurity. Number 5, the big 2023. So it could be as early as January we get a practical quantum computer. Now, in literature, most of this has stayed the same, so this is for reference. So basically, the big companies, you have Amgen, IBM, IEEE publication, Roche, QCware, and NIH. There's been a push with COVID-19 with quantum machine learning for it to go clinical. It hasn't reached that stage yet. And these are, again, for reference, these are some of the better quantum machine learning algorithms out there. So this, and then we have slide 2, and then we have slide 3 here too. So that's available in the pitch deck. Now, in this specific one, the key factors, so Los Angeles National Laboratory, sample complexity will favor quantum advantage. The Google, Caltech, Harvard. So again, this is more for reference, for basically newcomers to the material. This is for reference as well. And then this, I would definitely check a lot of these. There's been a lot as far as quantum technologies, and just, uncovering that quantum machine learning is the most common application for quantum computing. And then you have FDA approving a lot of these more deep learning algorithms this year as opposed to recent years. And then President Biden, Obama with support. Obama was in Chicago for, it's basically a Chicago Quantum Exchange. And then you have developments in internet, and then a bunch of the other companies that we're getting, Q-Control, Quantum, AWS. There's improvements being made across the industry, which is important for, to support healthcare operations. So you also have Intel, IBM, Quantum, and Google. They're Fortune 500 companies. I think most Quantinuum is Honeywell, and so basically there's 4 other IPOs in quantum so far. 3 of them have been multi-billion dollars or billion-dollar or plus. And you can see kind of the forecast, $850 billion by annual value by 2040. And then last year, 2021, 3.2. Now this year, is kind of tweener year. Next year is the whole forecast that we'll start to see a lot better applications. Now, this is basically regulations. So these are factors for, say your ISO, ASTM, and then in specific, IEEE Quantum, if you go on their website, it's in the bibliography here too, is you can click on these and they already have standards for quantum computer. They have standards for quantum algorithms, these types of things, software components. This one I'm going to touch on. So basically this is stage 2, and basically these are all the factors to getting better imaging. So again, where stage 1 is focused on, Alzheimer's disease prediction, stage 2 is focused more on better imaging. Either, this is basically at the sensor level or detector level. So a diamond quantum sensor, for instance, for data acquisition. Reconstruction algorithms, a lot of those exist for machine learning. So this would be perspective bumps. So the parts that you can go faster with quantum, you run on quantum hardware, and then the original parts you keep, and hence quantum transfer learning. And then enhancement, not as much. Analysis, segmentation, visualization. These are existing software platforms. Expect to see things as the years go on with quantum and healthcare, and then with management, internet. And then cybersecurity. I also included additional growth potential areas. So these go anywhere from GANs, generative adversarial networks, all the way to federated learning with radiomics as well. Now, this is the same slide again. It's just, in this part of the deck as before. And then basically the stage summaries, number A, or letter A, developments with existing image databases and quantum machine learning will present opportunities for Alzheimer's disease prediction improvements. Now, the key is the definition. Is a lot of these that you see, this, especially from this earlier article that I took a look at, is mild cognitive impairment to Alzheimer's disease. And there's, without getting into too much, but there's areas where that's lacking. Say if they pull some things away from researchers where they can't see any of it, your prediction might go from like 80% or low 90s down to like 50% was one of the studies. So, there's areas of improvement, it looks like. And then letter B, image processing steps with emerging quantum technologies can likely be utilized to create better brain images. So this is, so your neural image, is it clearer? Do you have better sensitivity? Do you have resolution or increased resolution? Letter C is basically this combination. So stage 1, stage 2, where you have this prediction algorithm that's better on stage 1, and then other areas that are feeding into making better neural images, which is more involved, hence stage 2. And then potential FDA submissions based on any of those stages. Now, the ChemicalQDevice mission statement is to improve neuroimaging techniques utilizing quantum technologies for better sensitivity, signal strength, and/or resolution combined with advanced prediction and neuroradiology for Alzheimer's disease. This can include quantum sensing algorithms and computing, and then MRI PET modalities. This is like, your brain picture with QML, neuroimaging techniques. So this is a good reference. So basically, I haven't come across too much with quantum computing and medical imaging. Now, medical imaging, its compound annual growth rate is about 10% higher. It's like 45% than drug. Keep in mind, there are likely companies taking closer. You still have, Fermi Lab and QSI, but these are a bunch of the startups. There's a lot of work being done in drug discovery. Now, in specific, this is current platforms. So this is Meredith, as previous IBM, Watson Health. And then these vary as far as, so say on the more fundamental aspect where chemical Q devices, a subtle medical looks at denoising for low count images. And then similar like Zebra Medical digitizing radiology scans, and Sirona, the first unified cloud platform. But there's a lot out there. There's a lot in specific of taking existing technologies and then stitching them all together digitally for the benefit of a radiologist. This is an option for FDA approval, is to go through this long process. They're called technology readiness levels. So it's a potential thing that the company can look at. Here's a bunch of the recent decks. All these links I'll show you coming up here. This is what's going on in the brain. So this, for instance, is a in recent years take of the amyloid beta plaques and tau fibro, the tangles inside the neurons. And then here's where you can see a bunch of the neuroscience news. And then I put in the references here if you ever want to check these out. They vary drastically. It's not, I volunteered at 2 inside San Diego October was the month for Alzheimer's walks in San Diego. So I did those 2. But it's just a very compelling thing as far as caretakers get up there and just say, that they had a loved one pass away, and then the next month they had another one too. So it's very interesting. So this, I didn't make too many changes to this, and this is basically saying this is perspective hardware. This is kind of how a lot of things sit today. The one I've been hearing more about is photonics at the bottom. And but I think by and large, the 2 kind of leading technologies are both ion trap and superconductive qubit. Now on this one, so I would definitely still check out this article, this big one in the middle. But the news this week, this week is basically Harvard announced, if you've caught a bunch of the previous discussion, there's a thing called quantum diamond sensors. Now, the way those work is you have carbon, which is a diamond, and you omit carbon and put nitrogen. So that leaves a vacancy. So that's called an NV center. Now, in this specific one, instead of nitrogen, they're using silicon. So this is silicon vacancy center. And due to the inherent properties of silicon, they achieve 2 seconds of quantum memory, which is like unheard of, so usually we're talking microseconds, sometimes milliseconds. So orders of magnitude better. This specific application is for communications, so quantum sensing, fiber optics, that kind of stuff. But you might start to see this potentially move into the whole, quantum sensing. You need quantum sensing, quantum memory for quantum computing too. So more than likely, somebody's working on a silicon vacancy quantum diamond sensor for those areas. Now, here's a bunch of the resources. I think there's 215. And keep in mind, some of these are from previous weeks, but if you ever want to take a look at a lot of these things as it goes through here, that's available. And then I appreciate everybody coming on. It's definitely, after that Thanksgiving, it's the survival of the fittest. I'm going to open up, let's see, we'll do chat. And then you'll be free to come on. You'll be free to post in the chat here, kind of interested on people's take with the quantum tech going into healthcare. And then, so we have some returning guests. So we have George and Ron. And then I think, Connor, you can come on as well, but feel free to unmute and show video. And then, definitely interested as far as the quantum aspect, what people think as far as, this upcoming year. It's not just medical. It's, quantum internet. There's so many different areas. And perhaps the biggest things that we've seen has been the diamond quantum sensor as far as applications, anywhere from, this goes from millimeter resolution instead of centimeter resolution off ECG, basically on a rat's heart. And then, going into, they've used them for batteries, for a better prediction of or better known charge state as you're driving down the road, that kind of stuff too. So it's definitely an interesting thing. Now, quantum sensors have been around since MRIs and lasers. They operate on somewhere along the way in their processes on the principles of quantum mechanics. Now, quantum computing is the new one to town because it's taking advantage of superpositioning and entanglement to get potentially better parallel processing and exponential performance. So, that's typically taking the bulk of the news, but it's always good to have a backup plan, like say if there's a holdup with quantum for some reason. But I think as especially this year with developments and now it's in Dell. There's Dell Quantum Solutions. So, but yeah, feel free to unmute if you have any questions. And especially so if we do chat here too, so chat. Feel free to post anything in the chat, and then go ahead, Ron.
Just had a comment on one of your slides. You were talking about Qiskit and Quasm side by side, or QSM, Quasm 2. I think you had it backwards. Qiskit, the language, is a Python framework as far as I can tell, and that's compiled into Quasm, not the other way around.
Oh yeah.
So Quasm is a Quasm stands
well, yeah,
for
they call it Chasm.
Chasm. It stands for Q assembly. It's closer to the hardware than the Qiskit language.
Okay.
That's my understanding. I don't know if somebody if you have a different sense on that, but a lot of the Qiskit, a lot of what goes on in Qiskit is actually below Chasm. The routers and the what they call the optimizers and the routers and stuff are layers of Qiskit code that is below that. So most people don't ever mess with that. They just let IBM do the best they can.
Yeah, I appreciate that. So I've come across some other kind of like they just do programming all the time. And yeah, I guess for those that don't know, so this is basically a free service on, if you're doing like quantum simulators or some of the lower hardware. And I that sounds right. Qiskit is Python based, and then OpenQASM is closer to the hardware. A lot of the code, there's a website called Papers with Code. And if you type in QML, standing for quantum machine learning, you can get these papers. And I didn't have much luck as far as copying, pasting. So this is where that goes into, you really have to know what you're doing, as opposed to like if they just give you a circuit and then you just run it and then you see what happened. So that's the biggest thing, because it's easy to understand the staff notation and gates and those types of things, and then actually doing something that's more productive, and you're taking all these things from several different papers and calling it your own kind of thing. That's perhaps a steeper learning curve. I put it in the chat here. It's this Harvard, and then if anybody else wants to come on, go ahead. The Harvard University paper. So it's the archive. So the archive is basically a depository. The paper that people know of is in Science, and then you need a subscription for Science. But it's worth taking a look at. It's all, the quantum sensing here is all directed towards telecommunications. So 2 seconds versus, like I said, microseconds or milliseconds is a huge jump. And the paper that reminds me of, there's a Google, Caltech, Harvard paper that basically says they used an original quantum computer from Google, say in 2019, and using quantum sensing and memory, those two together, is that it overcame all of the problems, or it mitigated some of the error, so it wasn't the principal component. So when I saw this paper, I'm thinking, what if they can start using this, say, for even Google's original 2019, quantum processor too. So I like what I saw. I didn't see anything saying directly, I think they specifically were focusing on quantum repeaters. So these are things in quantum internet. And it'll be interesting if we see that analog for computing. And so this is basically saying you don't have to fix the computers that much, and then you can overcome some of the limitations with quantum sensing and quantum memory. So it's worth taking a look at. And then George, did you have anything? So George has been on in previous calls, and then I would say he has a strong background in physics and kind of like the fundamentals. Go ahead, George.
No, it has been a bit much for me to digest this time. I'm not well informed on the medical side.
Yeah, it's definitely, they say if you want to have something good, you need to be an expert in multiple areas. So it was hard for me, I'd say, the first month to really dig into medical, and then go back to quantum, and then come back again, and then incorporate these to something that makes sense. So, but yeah, it's a learning curve. And was there anything on the quantum side that you wanted to talk about?
No, not so much newsworthy, thank you.
And then, so I see we have a bunch of other people that are new to the discussion. And then Yazin or Mike, feel free to come on.
Yes, yeah, interesting presentation. I have just one question. So regarding to imaging, for example, for the classification using algorithm from classical way. So how is there a way to using in quantum computing would be developing or merging like computer vision type to quantum computer. So how there is any transition to do that, or
yeah. So there's been some papers on it, or at least one, and basically it's called transfer learning. So there was there in the references, if you take a look at the deck, there's a paper this year, and actually I further explained it on this deck as well. Is basically they're leaving most of it the same. So this is your original conventional algorithm that you were using for classification. Now this paper was healthy control to Alzheimer's disease, which is an easier task, but hey, it's like proof of concept anyway. And then they're just changing a little part of it so that it's taking advantage of quantum, and in this case it's a Pennylane simulator, where it makes sense. So that's how you're going to see it, Yassine, is basically anything that's quantum related is going to run on quantum simulator, meaning you have a classical computer, but it's running quantum. And then, or everybody really wants it to work on a quantum computer. And then that's what's kind of getting worked on now. Say for instance, with IBM, error mitigation and suppression. But yeah, that's the approach right now. There's at least that one paper, it's in this deck, and you could take a closer look at it. But basically, I don't know if you know ResNet 34 structure. It's the one where I showed it went from like classical to quantum, to classical. So using those, it's fine tuning, and to get the highest quantum advantage, obviously you'd have like quantum data, quantum sensor, quantum memory, and then quantum computing. But more than likely, at least in the next year, I would say it's going to be this hybrid approach where you just alter something, not the whole thing, but a specific part that doesn't do well conventionally, and then that's where you try to get advantage.
Makes sense. Yeah. Thanks.
Yeah, and then so Connor is going to be all that capacity. Yeah, so basically, Connor, a lot of these things are likely gonna keep conventionally. So I was using that example to say to get quantum advantage. A lot of the storage and likewise, at least in the near term, will likely remain classical, and it's just doing bits and pieces of the things that make sense to use quantum, use it quantum, and then it has to be interoperable with classical, and then this is the whole hybrid kind of stuff. Did you have something else, Ron?
I was just thinking about this whole imaging, getting into the ability of doing the research of using stock images, either from MRI or wherever they come from, and getting into QML to see if you can do better predictions. I'm starting to wonder, what's the cost of entry there? I mean, what groups are doing it currently, and like what kind of budgets are they running with?
Again, it's the same paper. It's so most of these are ADNI. So ADNI is Alzheimer's Disease Neuroimaging Initiative, and then so they've had like 3 or 4 stages where, say, their original was just MRI, and then their next one might be, it's called PET, amyloid beta, and now the big thing is called PET, tau PET. But they're trusted. It's just the concern with that is the data sets need to be bigger and more diverse, but it's quality data as we see it. So and again, it's this paper. So even there's a gentleman, Bren Raw, came on it, and he resent it to me after I reviewed it the first time, and it seems to be interesting. This is the 97% quantum versus 92% conventional approach. So I would say that one, and then the other paper that I took a look at today, as far as the last 10 years of classifying between MCI to AD, and then this isn't quantum at all, and then find out what works there, and then you look at all the specific processes. So I'll probably cover this next week because I've been uncovering it, but you'll look at what does work for classical, keep it, and then the parts that are slow or not possible with quantum, and that's I think in that kind of like breakthrough area.
Right. I mean, classical machine learning has probably been after these images for a long time, and it's just a matter of bringing in a quantum classical hybrid, so that you can take advantage of the quantum advantage and get things to either get better or faster or something. But I guess what I'm thinking though is some of this data that's out there, is that freely available? If you like, anytime you start talking about large data in machine learning, you're talking about lots and lots of number crunching on the classical side, and then how much can the quantum actually do as of today? Every day it'll get better, obviously, but what's the cost of entry to actually fire up a research project and try to make a difference?
It's this paper. So
this one, the one that you posted in the chat?
Yeah, so it has qubit map. So you start off with Resonat 34 classical architecture, and they're saying for this specific task, the variational quantum classifier, you're doing it that, and then they're using a plain quantum simulator, Pennylane, and then it's an in-depth paper, and it also explains how they did it conventionally. So using their methods without quantum, 92%, using their methods with 97%. So obviously this is like a beginning of a new era, and then so all of that will likely have to be more scrutinized. So it is interesting because, like, yes, you want to compare apples to apples, like your same setup, classical versus quantum, but how does that compare to the best classical external, right? So there's all these things there's nuances in the papers where you really have to see, like, okay, why did they do this? What was the advantage of doing doing that process conventionally and now switching over to a Pennylane simulator. Now, cost-wise, what you were asking, I think that if it's working well with simulator, it's just it'll go likely under a lot more scrutiny, because you'll say, okay, well, how does that compare to this other conventional one? And if they're not apples to apples kind of thing. But I would say it's encouraging results, and actually to have Bren send that to me. And that was after I reviewed it previously, and now kind of like making sense of it all.
Yeah, Dr. Beren was interested in using QML to attack public DNA databases. He was interested in inserting a quantum enhanced neural layer in a machine learning stack. But I think a lot of the problems you run into is a lot of these things where you want to use the transfer learning, those tend to be the lower layers of the stack. So you generally want to leave those alone and do your extended processing downstream. So he was having issues getting his quantum enhanced neural layer installed in the middle of a stack.
Oh, okay.
So it's pretty interesting.
Interesting. George, did you have something?
No, I just wanted to comment that Barond is very impressive in being trained in both medicine and physics.
Yeah, and again, I appreciate the comment for sure. So I don't think I had Bren on before, but he's definitely been on this discussion before, and he asks really good questions. I think it's just probably the middle of the night for him.
I think
that's probably the thing there.
He was wasn't he one of your speakers like 6 months ago?
Oh yeah, he did DNA Bert.
Yeah, that's what I was talking about. He was.
Yeah.
And I actually had a conversation with him after that fact and tried to give him some pointers on how to get his machine learning stack to accept a custom layer.
Okay.
So, I don't know, but then I didn't hear anything more from him. But again, it seemed like because he's trying to insert the quantum down, really far downstream. It seems like the quantum stuff seems to do better on the front end, where the optimizations can be more effective. So I'll have to get in touch with him again and see how he's doing, see if he made any progress there.
Yeah. Anybody else we haven't heard from, Risky or Mike?
I got some. I could add something, or I don't know if I can add something, but I have some of my confusion is, does the simulator have the error rate problems and the extension problems and memory addressing problems that the real system has? And my understanding is if you have in the simulator, you can probably only use like 12 or 20 quantum bits, qubits, and to be the practicality is, and you don't have error rate in fishing and addressing it. In the simulator, you can, the compiler and the environment work like a real, like it was real memory. And,
Right.
And when you get to a real quantum thing and you have, let's say, 48 bits, 48 qubits, you could get, that supposedly could give you 2 to the 48th separate memory addressing, but you can't get, you can't get to them without errors. And is that error rate going to require some other way? Is the compiler going to handle all that for the environment, and the compiler going to help you do that so you can treat it like a ordinary Dell computer or an ordinary computer?
Yeah, I appreciate that question. So it's a thing worth going over. I've heard the most today that you could do to simulate is 30 qubits. And then, quantum simulators don't have error, and they don't have much power relative to like these theoretical advancements of, say, if you have like 50 to 51 qubits, you're doubling information. And if that's practical, meaning that there's not much noise. So it's just a thing. So going back to this paper again, it's, they're using a Pennylane simulator. And I'd have to go in more in depth as far as how many qubits there. Now, when you were talking, it just reminded me of, they say, oh, we'll never have quantum memory. I remember that was like a pretty much accepted thing. And here we are at 2 seconds. Now, it doesn't sound like a lot, but, it's an improvement.
In the simulator, you're at 2 seconds, or in real quantum memory, you have even a 6-qubit machine still has the error rate problem, even though the simulator doesn't.
Well, yeah. So the quantum memory would be for respectively real quantum hardware. The quantum simulator is basically an errorless environment, but it just doesn't have that. So the quantum mechanics in a quantum computer, the number one, you have parallel processing due to the superpositioning, but with entanglement, that's what gives you that quantum advantage, quantum supremacy if we didn't have error in the real quantum computer. And then, Mike, did you have something? Or actually, Lakshmi, we haven't heard from you. And then anybody else, you could feel free to come back on. And yeah, so it's definitely exciting times. I think that what resonates most with me with the deck is this, where you go through and it's one of the earlier slides, and you're basically saying, oh, okay, here's the timeline, here's what we need in healthcare, here's what's going to be the result. Because ultimately you have to understand that the people around you haven't done the research you have. And breaking things down into simple business diagrams, basically, those types of things too. So anything else? Any other questions or comments?
Is this and some of the previous ones, which I missed most, it sounds like you have several of these. Are they out on someplace I can look at them?
Yeah. So if you're on LinkedIn, and then I'll pull it up real quick. So it's basically the channel on YouTube, and I'll be posting this. Let's see.
Slides?
Yeah, I always reference the slides, and here's the channel. So I'm going to put videos in chat. So that'll take you to videos, and then on the decks, I usually reference, it goes back to the websites first, like the physical decks. So, and any other last questions?
Thank you.
You're welcome. Appreciate everybody coming on. Once again, this is episode 59, December 1st, 2022. Looking forward to more quantum advancements for prospective medical use. Thanks everybody for coming on, and have a good, productive rest of your week. Take care.